Hey, good morning, Calculus 1. Welcome back. We're moving into the rest of Chapter 3. Remember, 3.1 was still doing derivatives with that limit definition. And the rest of Chapter 3, we start learning some shortcuts, some new rules for derivatives. So that's where we start here in Section 3 too. So, to me, that's the start of Chapter 3 in a way, because I included 3.1 in the Chapter 2 topics, the limit topics. So, doing a derivative, the one word for that is doing a derivative or differentiation, the process of finding the derivative of a function, differentiation. You know, here's a little notation. If the function is f of x or y, then we take the derivative and we call that new expression. It's a new function, by the way. We call that f prime of x or y prime. Or we use this dy dx. We just say dy dx. It's kind of dy over dx, but we say dy dx. The derivative, it's the derivative of the function y with respect to x. You know, sometimes in higher level calculus, calculus 3, we have more than one variable. So you might take the derivative of y with respect to some other variable. Or you might, those are called partial derivatives. I'm not really ready to teach that. That's calculus 3. But I'm just trying to explain the wording. The derivative of y with respect to the variable x. Sometimes it's good to identify what the variable is. Sometimes that we don't use x. Sometimes the variable will be t. We'll do dy dt. So the derivative, the limit definition was this limit definition. We got good at that. That's always in the background. It's good to know that, but we're going to move on. We're going to start doing derivatives a new way. And then, again, I call that the mathematical definition of what a derivative is. The limit is delta x goes to 0. But the English definition is also important. What is a derivative? It's the slope of the tangent line. Some students think, oh, it's the tangent line. Sorry, it's not the tangent line. It's not the equation of the tangent line. That's important. But it's the slope of the tangent line. It's a new formula that tells me the slope of the tangent line to the function at any point x. So it's kind of a general slope. And what is a slope? A slope is a rate of change, but it's not an average rate of change between 2 points. The derivative is an instantaneous rate of change with respect of one variable with respect to another variable. So a lot of good language here, but let's get to some rules here. So if we go to 3.3, here's a rule. If your function is a constant, the derivative is 0. So there you go. And so this is one way to write that rule. Y is some constant function c. There's no variable x there. When I take the derivative of y, I get a 0. Now let's explain that real quick. One way to explain it or prove it is to go back to this limit definition and prove it with a function that's just called c. And you could prove that, I could prove that. Another way to prove it is think of it visually. What is a derivative? It's the slope of the tangent line. And if the function is a constant, so sometimes I like to think visually. If the function is a constant, here it is. It's y equals c. You know, if it was y equals 4, it'd be right there at 4. It's a horizontal line. Let me ask you this question from algebra. What's the slope of a horizontal line? 0. What I want is the slope of a tangent line. What would be a tangent line to this line? It's kind of weird. When this is a line, the tangent line to that line is that line. And what would be the slope of the tangent line? The derivative would be 0. So some things I over-explain, or we can over-explain, but that explains it pretty well. I want to say this. The way we write this rule is this. So I wrote it like this, but the way we write this rule is like this. The derivative with respect to x of a constant is 0. And sometimes I think that could be confusing to students. I'd like to point out that it's kind of like I'm using this notation. But there's no y, or yes there is. The y is that function c. So it's off to the side there, but if it's off to the side, it's sort of in the numerator. So I'm taking the derivative of my y, but my y is my constant function c with respect to x, and the answer is 0. So this is kind of the way we write our rules. Here, I'll write you another one. what is the derivative with respect to x of this function, x? And I can tell you the answer. The answer is 1. I could explain it. I could go do the limit definition and prove it. That's how we learn to do it in chapter 2, or section 3.1. I could talk like this. I could say, oh, visually, this is a function called y equals x. It's a line called y equals x. There's a picture of it. What's the slope of that line? 1. Well, hang on. What's the slope of any tangent line to that line? 1. I mean, any tangent line to that line is that line. So this only gets a little more interesting when you have curves, and then the tangent line is changing and the slope is changing. That means it must have a variable in its answer. So I'm trying to convince you of some of these rules. Here comes the big one. These are kind of trivial, easy ones. Here comes the big, important rule. It's called the power rule, and it's the rule that says, what's the derivative of x to any power n? So the variable is x, and it's like an x squared, an x cubed, an x to the half, an x to the -2. This is awesome. Here's the rule. You bring the n down, and you multiply by the variable x, and you subtract 1 from that power, x to the n minus 1. Okay, I can't explain that visually to you. I could prove it to you using the definition. I might do that in a future video. I think you can look at the book, you can read the book, you can see that. But this is big. This is the power rule for derivatives. It's called the power rule. I mean, let's just try an example. I mean, this is what I've been waiting to tell you. I've been waiting to teach you this rule. We had to get through chapter 2. We had to get through limits. I've been waiting to get here. This is the power rule. This is what we use. This is big, big time. If I have an x cubed, what's the derivative? According to this rule, you bring the 3 down and you subtract 1 from the power. You're done in 2 seconds. You sure don't want to do it like this, do you? 2 seconds. You bring the 3 down, x squared. And what is this? It's the derivative. What is it? It's a little formula that tells me the slope of the tangent line to this function. So this is a function, it's a curvy function, and its slope at any point is its own function. It varies. The slope varies on this curvy function. So the slope has a variable in it. You know, if I'm at x equals 1, the slope is 3. If I'm at x equals 2, I plug in a 2, and the slope is 12. It's pretty steep. If I'm at x equals 4, I think that's a 48. 4 squared times 3. So the slope is huge. All right, let's get to some more rules. And we'll have to, there's a lot to tell you. Here's a rule. The derivative of any constant k times a function f of x. I guess I could use a c. We used a c for a constant up here. C is a constant, k is a constant. Variables are x and t and y. Anyway, when you have a constant multiplied by your function, then this rule says that it's the constant multiplied by the derivative of the function. To take the derivative of a constant multiplied by your function, you just pull the constant out front, and it's the constant multiplied by the derivative of the function. That's kind of a powerful rule. Here's another one for you. The derivative of a function, f of x, plus added or subtracted to another function, g of x. So when I'm trying to do the derivative of one function plus or minus some other function, what do? And maybe you think it's obvious. You take the derivative of each function separately. But, maybe I don't know how obvious that is. Somebody needs to tell you, these are the rules for doing derivatives. Here we go. It's kind of like the rules for doing limits. What did I say? You just do the derivative of him, and you do the derivative of him as 2, and you add or subtract. So it's this. The rule is stated like this. F prime of x added or subtracted to g prime of x. These are powerful rules. In conjunction with this power rule, this is almost like a power rule here. This x, you can think of x as x to the first. And what would be his derivative? We've got to watch out for firsts and primes. This is y prime, the derivative. How would you do this derivative? You bring the 1 down. Using the power rule, you would bring the 1 down. X, you would subtract 1, you'd have x to the 0. Everybody knows that x to the 0 is a 1. So, guess what? That's a 1. I mean, we talked about that before I taught you the power rule, but the power rule applies. Okay, all right, we're getting there. Let's get a few more rules up here. That's the good. I think that's most of the basic rules right there. Again, this one's important. All these are important. I want to show you how we're going to use these in just a second, but let me spit out a few more. If I'm in section 3.2, I think they go ahead and tell you this rule, the derivative of the sine function. So the derivative of sine x, and guess what? The answer is cosine x. That's kind of hard to prove. If I was to prove that to you, so right now I'm telling you these rules, and you should just say, okay, thank you, I'll believe these rules. But if you're questioning why is that, you need somebody to prove it to you, or you need to prove it to yourself. And the way to prove it to yourself is go do this. If you do this for a sine function, the result will be a cosine function. The book does it. You could read about it. I could do it for you sometime. Right now I'm not going to. The derivative of sine of x is cosine of x. We need to memorize these rules. Here's another one. The derivative of cosine x is negative sine x. The derivative of cosine of x is negative sine of x. Here's another one. The derivative of the e function. The derivative of e to the x. You know, that's not going to follow the power rule. It's different. You know, the power rule is a variable in the base with a number in the exponent. And that's the power rule. An exponential function is not a variable in the base. An exponential function is a number in the base, and the variable is in the exponent. It's a different category of functions. And it has its own rule. The derivative for e to the x is himself, e to the x. It's not the power rule, it's its own rule, and it's kind of a funny little rule. The derivative of the e function is himself. There's more to say. You know, there are more trig functions. They come up in the next section or two, so I won't put them here. We're in section 3.2. These are sort of the foundational rules, but there are more trig functions. I could tell you those rules. You know, there's the cousin to the e function is the natural log function. It has its own rule. That comes up in a little bit later. So I won't spill all these rules out here quite today. But that's it. I mean, there's those few more rules, and well, there's several more rules coming. But this gets us started in section 3.2. All right, so let's do. Well, I'm going to erase some of this stuff. I want to do one problem here for you. And I'm going to do this problem a little funny. Here's this function, y equals 5x cubed minus 7x squared plus 8x minus 11. And I want the derivative. And I am going to do it because this is the first time I'm doing this. I'm going to kind of show you how I'm going to use this rule, and this rule, and this rule. I think I'm using all these rules. There is no sine or cosine or e function, so I'm not using those. But I think I'll be using all these rules. So watch what I mean here. If I want to do this derivative, first of all, it's one long function, but I guess according to this rule, I'm allowed to do the derivative of each term separately. These are terms separated by plus and minus signs. So I can think of this as its own function, and I do the derivative of each one of these separately. Okay? And so, you know, this is kind of how, do not write this. This is the long way of writing this. I'm doing the derivative of that guy, minus, I'm going to do the derivative of this guy, 7x squared. I'm going to do the derivative of this guy, which is an 8x. And then I'm going to do the derivative of this 11. Work my way into a corner over here. Sorry about that. That's okay. All right. So I kind of applied that rule. It said, I'm doing the derivative of this polynomial with all these separate terms, but I'm doing the derivative of each term separately. Okay, now I'm going to use this little rule that says, well, what do you do with these multiplied constants? Like, what do you do with this 5? What do you do with this 7? What do you do with this 8? Oh, you can just sort of slide them out front. So in other words, I take the 5 out front, and then I can do the derivative of the x cubed. A multiplied 5 can kind of slide out front. It's not an added 5. That multiplied 7 can sort of slide out front, and then I can do the derivative of x squared. That multiplied 8 can slide out front, and I can do the derivative of the x. And I guess I could pull the 11 out front. The truth is, let's go ahead and do this one. What is the derivative of the constant 11? What is the derivative of the constant 11? His derivative is 0. So I went ahead and did that derivative. I haven't really done any of these other derivatives yet. I just applied these two rules. I think I'm ready to go ahead and do the power rule now. Here we go. I'm going to do the derivative now. I'm going to do the derivative of this x cubed. And according to the power rule, you bring the 3 down, and it's a 3x squared. And the 5 is waiting out front to be multiplied. I'm going to do the derivative of x squared. That's going to be bring the 2 down, subtract 1, you've got x to the first. That's the derivative, and the 7 is waiting out front. What's the derivative of an x? We had its own little rule, but it's kind of a power rule. We know it's a 1, so that's an 8 times a 1. We've already got that done. It's a 0. Hey, you can multiply these back now. So the final answer is 15x squared minus 14x plus 8. That's a long polynomial function. That's the derivative of this original function, 5x cubed minus 7x squared plus 8x minus 11. His derivative is this. It's a formula for the slope of the tangent line, and we know all that. And I did it this long way to try to illustrate the use of these rules. The truth is, I swear to God, I'm going to erase something down here for you. In real life, on a test, when you have this question, you don't do all that. You don't need to write all that out. When you do this derivative, it's kind of like you're doing all those little rules in your head. I mean, you hold the 5 out front, you do the power rule, and then you put the 5 back, but you can do all that in your head, and you get 15x squared. I mean, you bring the 3 down and multiply it by you get 15x squared. Subtract 1, you get 14x. Subtract 1 from the power. You get the 1 times the 8, you get an 8. The derivative of a constant is 0. So that's how you do derivatives. I did it this long way to illustrate the use of these rules. It really wasn't a waste of time, but I won't do it like that anymore. All right, thank you for listening. That's a lot of information in 3-2. You can attack some homework. Well, I actually need to help you with some other stuff. All right, I'll be doing another video. All right, bye.